Let's just change this filter. Uh, hue shift. Yeah. Purple. Yeah. Alright, let's fucking go through. I'm looking up confinement and asymptotic freedom of quarks. This is some quantum mechanics shit. Way above your fucking head, yo. But we gotta digest.
As previously discussed, quarks always come in groups. For example, if we examine the baryon particle, baryons always consist of 3 quarks. And if we examine the mesons, the internal structure of the meson consists of a pair, a quark-anti-quark pair. So we see that quarks always come in groups. And our inability to actually experimentally isolate, observe, and examine an individual quark is known as quark confinement. So quarks are always confined to existing in a group rather than as individual species. Wow. Now, one way that helps us to visualize quark confinement is by imagining that our quarks are confined to an elastic bag that can be stretched, but to
hold up, you're fucking loud as fuck, dude.
Stretch this bag, we actually have to input a great amount of energy, a great amount of work. So let's take a look at diagram A. In diagram A, we have one type of baryon, the proton. So the proton is shown by this outer circle. And we can imagine that the outer boundaries of our proton serve as this elastic bag. And to actually stretch the elastic bag to separate the individual quarks, we have to input a certain amount of work into our system, our proton. So basically, inside this proton, we have 3 quarks. So we have the up quark, which has the color red. We have the other up quark that has the color blue. And we have the down quark, which has...
And then he's going to get into detail about how the charge of the up quarks is 2/3 positive and the down quark is a negative 1/3. And the fucking shit that I get tripping over is like, in the Bible, they say that the kingdom of heaven is like 2/3. And other stuff is the third. So it's like in our nature to think of shit that way. In my nature, bitch.
Has the color green, and each one of these colors produces a color charge. It gives the quark's color charge, and when the blue ones, the fundamental particles that carry the strong force, also known as the color force.
Yeah, the cold force, yo. You know I'm being mad cold, yo. I fucking love it. I love weed. I really enjoy cannabis. This was in May 3rd, 2014. I probably took some finals in college at that time. I was class president. That's an epic thing. And I was finishing up a semester to prepare to go abroad next semester to India.
When they exchange the gluons, that basically holds our quarks together within our proton.
So
now,
me and him are the
let's
proton
actually
right
suppose
now.
we
Whatever the fuck we
try
doing.
to separate our quarks from one another. Let's say we want to separate this blue up.
If I was going to be rude, I would just talk over him. But I'm going to let him talk. He's probably going to tell you in some fucking way that I might even get another idea. It depends. How we quirking.
Quark from these other two quarks. So we try to actually input a certain amount of energy. We try to do work on our system to separate our quarks. So it actually turns out that a tremendous amount of energy, of work must be done to actually overcome those strong nuclear forces, those color forces that hold our quarks together. Now, it turns out that when we actually input that tremendous amount of energy, the amount of energy that we input to actually separate and stretch our elastic bag ends up exceeding the amount of energy that is needed to actually form new mesons and baryons via the process of pair production. So remember, pair production is basically using energy to transform energy via Einstein's mass energy equivalence principle, converting energy into mass. So recall that we can actually use energy, and if we have a great amount of energy, we can readily transform that energy into forming new mass, new particles. It turns out that nuclear must be done.
Is he trying to tell me you can turn energy into fucking matter? What? What if I just talk?
To actually overcome those strong nuclear forces, those color forces that hold our quarks together. Now, it turns out that when we actually input that tremendous amount of energy, the amount of energy that we input to actually separate and stretch our elastic bag ends up exceeding the amount of energy that is needed to actually form new mesons and baryons via the process of pair production. So remember, pair production is basically using energy to transform energy via Einstein's mass energy equivalence principle, converting energy into mass. So recall that we can actually use energy, and if we have a great amount of energy, we can readily transform that energy into forming new mass, new particles.
You got me lost, dude.
And baryons via the process of exceeding the amount of energy that is needed to actually form new mesons and baryons via the process of pair production. So remember,
right. So just to explain why that was probably so hard. One, I was grinding up weed. This is my strong force right here, me and this weed shit. So I had to rerun that a couple times I exceeded the amount of input to stress that. But yeah, he's right.
Production is basically using energy to transform energy via Einstein's mass energy equivalence principle, converting energy into mass. So recall that we can actually use energy, and if we have a great amount of energy, we can readily transform that energy into forming new mass, new particles. And it turns out when we input this great amount of energy, we input an amount of energy that exceeds the amount of energy needed to produce new mesons, the quark-anti-quark pairs, via pair production. And this means instead of actually separating our quarks, we end up producing more mesons and more baryons, so we produce more hadrons.
Hold up, wait, what's he describing right now? I literally just did that. he was talking about how I was flipping the screens. So not only we got these two screens right here going, the video and Einstein's energy principle. Just a little something for you to scroll. You can't really see it, but it's there.
Visualizing quark confinement is commonly known as the bag model for quark confinement.
Quark confinement. So this confinement of a quark is, I'm in my bag.
So, one other concept, idea that I want to discuss in this lecture briefly is known as asymptotic freedom of our quarks. So, based on experimental evidence and experimental results, we see that as the quarks actually get very, very, very close to one another, so when they get close enough to form our proton, we see that the color force or the strong nuclear force that exists between these quarks actually ends up decreasing, and they can actually now move with a great amount of freedom around the space of the proton. And this idea that as the quarks get extremely close to one another, the force decreases between those quarks is known as the asymptotic freedom of those quarks. Now, of course, as the quarks begin moving away, that force begins to increase once again. So this idea of our quarks being able to actually move within this confined region of the proton with a great amount of freedom in their motion is known as asymptotic freedom, and it is a result of the fact that as they get close, that color force, that strong force that holds those quarks together begins to decrease, and that allows these quarks to move away. Now, of course, to move around. Of course, when we separate them, this force increases, and they want to snap back together to form back our proton. So when we try to stretch the bag, the color force, the strong force begins to increase, and so we see that a great amount of energy must be inputted to actually separate the quarks, and because the energy is so high, when we try to input that energy, we simply end up creating more mesons and more baryons as shown in this diagram. So these are our two examples of mesons that could be created for this particular case.
Fuck yeah, dude. Yeah, let's fucking... I can't look at an atom. Let's just look at my suggested. Whoa. What are these guys doing? Owning a Titan II missile silo? What?
Hey guys, welcome back to Atomic Underground. This is Season 1, Episode 9. It's opening the Escape Shaft version 2. So, we're going back here. This is still in December. This is Colby and I were down on Level 3 of the Launch Control Center trying to open up the Escape Shaft door. And we've been working on it for about an hour and a half. The threads, especially on the top there that you can see, had a bunch of rust and stuff on them, and we didn't have the proper tools. And running this thing for...
I didn't even know you were doing that. Sorry.
What is that?
Sorry.
I was like, I don't know, about that time. My watch isn't set to. It died on 16:54. About time to wrap it up.
4:54.
Damn.
That's pretty epic, dude. Random video of the day. Alright, let's see if this dude's talking to
Daniel
him.
here who got me on my insurance. Daniel, State Farm offers
Gravity
surprisingly great rates.
superhighways.
Nearly 20 years ago, NASA produced this beautiful image called interplanetary superhighways. This image illustrates that we believe that there are these very unusual and very interesting space manifolds or space formations that can essentially provide a very interesting way for us to travel from one planet to another.
Wow.
But after 20 years, we still haven't really discovered what they are and haven't really found a good way to essentially predict them. Hello wonderful person, this is Anton, and today we're going to be talking about a relatively recent study that might have actually discovered at least one way we can sort of predict these manifolds, at least to some extent. And this interesting study might actually one day allow us to travel across planets, or across the solar system that is, in a relatively quick and also relatively cheap way. But let's actually discuss this in a little bit more detail because there are a lot of things here that, well, we frankly don't really understand just yet. And to try to understand all of this, I guess let's start right here. We know that black holes warp space around them. You can obviously see it right there on the screen.
Yeah,
This is a space
I'm a
warping
black
effect
hole.
created by an extremely massive and compact object.
Yeah.
But we know that anything that has mass and energy produces these ripples, although they're not usually that easily visible. And the more complex the system, the more space folding and different types of manifolds end up forming in the region.
Right.
Now, one of the best examples of this so-called space manifold, or the formation of these very peculiar gravitational effects that kind of cause the space to produce unusual effects, at least for the solar system, are what's known as the Lagrange points. These are very stable orbital points that are kind of cause the space
Lagrange
to produce
points?
unusual effects. At least for the solar system, are what's known as the Lagrange points. These are very stable orbital points that are created by the interaction between two massive objects, in this case, the Sun and Earth. And these 5 points create 5 very specific regions in the orbit of a smaller object orbiting the larger object, where we can place another object to be in the same orbit as the smaller object. So in this case, if we were to place, for example, some sort of a large satellite right here, or right here, or right here, it would be able to orbit along with the Sun and not destabilize and, for example, get kicked out of the solar system or fall back onto planet Earth. And these, in essence, are these space manifolds, which in this image you can
Who's
see
trying to
usually
kick me
are
out of the
created by the
fucking solar
interaction between.
system? What? Is he trying to tell me that there's satellite consciousness of me right now everywhere? I mean, yeah, that's a crazy way to think, but realistically, he's on to some shit, yo. I guarantee this is some cool shit. Something about the point.
In the Earth and the much more massive Sun. And theoretically, we've discovered these objects many decades ago, with the first satellites to use these orbits being this beautiful satellite known as ICE, International Cometary Explorer. And back in 1978, it was placed in the L2 Lagrange Sun. And theoretically, we've discovered these objects many decades ago, with the first satellites to use these orbits being this beautiful satellite known as ICE, International Cometary Explorer. And back in 1978, it was placed in the L2 Lagrange point, which is roughly around 1.5 million kilometers away from Earth, toward the sun.
Ooh.
But if this is what you get with two different objects, what are you going to get if there are more planets orbiting around the sun?
Right.
And this is where the complexity begins. And also why NASA created this image 20 years ago. Even back then we understood that there's a lot of complexity and a lot of interconnection between different planets. It just we're not entirely sure how to calculate it yet. So the more planets there are, the more complex these space manifolds become. Now, if you want to learn more detail and more mathematics in regards to this, there's an entire article about this that I'm posting in the description. It's a pretty complex and actually somewhat difficult topic, and there's a lot of math in it, but it is interesting nevertheless. But when it comes to the solar system, some of the biggest and essentially most influential manifolds are formed through the interaction of Jupiter with the Sun and to some extent Saturn and the Sun. And so these manifolds actually do form something extremely influential in the solar system, something that extends all the way to Neptune but also influences the internal parts of the solar system as well. And there is a mathematical way for us to try to simulate all of this and to try to essentially visualize all of this by using what's known as the fast Lyapunov indicator, also known as FLI, which is a very interesting and a very mathematically thorough way to try to create different space manifold structures and to literally detect chaos in a very complex system. In other words, it's a way to sort of visualize and to simulate an extremely chaotic structure that has some sort of a space manifold or other manifold formation. And what this particular study that you can find in the description below decided to investigate, and also what essentially the study discovered, is the creation of various unusual formations, in this case space manifolds, by various planets as they interact with one another and as they interact with Jupiter and the Sun. And these manifolds, through the mutual interaction with the planets, can create these unusual structures, unusual tunnels, or in some sense highways that actually encourage and influence what in some ways we can call chaotic or chaos transport. In other words, they create a kind of a tunnel-like structure that does change with time, where it's possible for an object to transfer between two planets relatively quickly with practically no energy loss whatsoever. Now, naturally, this doesn't mean that we just discovered a way for us to get from Earth to Mars in like a week or so. That's actually not at all what we've just found. What we did discover, however, suggests that it's possible for a typical object like an asteroid to move between Jupiter and Saturn in just a few years with absolutely no energy use. And this, in some sense, at least hypothetically, can become a way for us to transfer between planets much quicker than previously. So even though it took Voyager craft approximately 12 years to get to Neptune, if we were to find a way to exploit these space manifolds, and if we were to find a way to precisely calculate the most efficient orbit or the most efficient path to Neptune using these space manifolds, it might save us a few years of time, possibly even helping us get here within only about 5 to 6 years. So ultimately this could result in our understanding of how to create, basically a super highway across the solar system, where we can now start saving years and years of travel and also a lot of fuel at the same time. But even though we're kind of still far away from that part, this also can help us understand why, for example, certain comets, especially the objects we often refer to as the Jupiter family comets, can often change their orbits quite dramatically, moving from the outskirts of the solar system to the inner solar system, which we today believe is actually directly related to these space manifolds. At the same time, a lot of different types of gravitational instability, like for example of these objects that you see in green, known as centaurs, can obviously be explained by the interaction of these different space manifolds. Some of these objects stay relatively stable for at least a few 100,000 years, but some of them can only be stable for a few decades. And it was very difficult for us to explain why some of these centaurs end up becoming...
And that would make sense, because Mercury is a communication planet, so the closer it is to the sun, the more like you can fucking talk and run your mouth. Things like love and fortune and Jupiter and Saturn, those things, not even love, wrong word. Yeah, they're fucking longer away. It takes
comets and coming closer to the sun itself. And now, using the theory from this particular paper, we can obviously explain it as one of these objects just going through one of these interplanetary highways and being guided through these tunnels,
Yeah.
coming closer and closer to the sun. And a lot of these simulations from
Closer
this
to the
paper
sun.
basically showed that Jupiter is the most influential creator of these interplanetary highways. These space manifolds, for the most part, are formed by the interaction of Jupiter and the Sun, and some of the secondary ones do form through the interaction with some of the other massive planets as well. Now, the thing is, none of these manifolds, none of these tunnels, if you want to call them that, stay stable. They do destabilize and they do change with time, which of course is related to the orbits of the planets around the Sun itself.
Right.
But being able to calculate where, for example, the next large manifold will appear that we can actually use for example, a transfer of a spacecraft to another planet is basically what all of this is about. Or at the same time being able to predict if one of the distant trans-Neptunian objects becomes sort of embedded in one of these systems and then gets transferred to the inner solar system. In other words, this can allow us to predict orbits of objects a lot more precisely than we currently can with the current technology. And it can also, of course, help us predict any potential collisions with some of these large objects in the nearby future. Now, we know that nothing major with a large manifold will appear that we can actually use for example, a transfer of a spacecraft to another planet is basically what all of this is about.
Wow.
Or at the same time being able to predict if one of the distant trans-Neptunian objects becomes sort of embedded in one of these systems and then gets transferred to the inner solar system. In other words, this can allow us to predict orbits of objects a lot more precisely than we currently can with the current technology. And it can also, of course, help us predict any potential collisions with some of these large objects in the nearby future. Now, we know that nothing major is going to happen to planet Earth, at least in the next few hundreds of years, but being able to use this new understanding of these space manifolds can help us predict this maybe even up to a few thousand or even a million years. And that's something that's sort of important for us, at least if we expect to somehow protect our planet for the next million years from these relatively dangerous collisions. But unfortunately, even in this study, the actual predictions and, in some sense, calculations are not really that thorough and that precise yet.
Yeah,
a lot of it was still based on simulating particles, for example, orbiting Jupiter. In other words, it was somewhat similar to what I just did right here using Universe Sandbox. By placing the Sun in the middle and a few massive planets, in this case I placed 2 Jupiters, whose orbits you can see right here, and then adding a few particles, in this case a few hundred particles, we can sort of start seeing how some of the particles do end up really far away from everything. Which I guess is a little bit easier to see if we change the background.
Right.
And a lot of these particles that got really far from the system, they basically went through these space manifolds and ended up getting kicked out of the inner star system.
Yeah.
And so this is right now maybe one of the few ways we can kind of try to analyze and study these space manifolds. Because unfortunately there is no precise way of doing this just yet. These are still extremely complex systems that require a lot of calculations. But studies like this do serve as a kind of a pioneering project for us to eventually figure out how we can calculate all of these really complex interactions and thus find an extremely efficient way to travel across the solar system, where a single travel from one planet to another might actually take much shorter than it would be otherwise possible.
Maybe
thus
you're not
obviously
the
allowing
right
us
guy
to
to be
send
talking
more
to right
missions
now.
to faraway distances,
What
but
do I
also
know you
hopefully
know?
one day colonize other objects. But for now, we don't really have a really good system to do this just yet. Even though originally NASA sort of proposed
They
it to be
fucking
otherwise possible,
colonize
thus
humans.
obviously allowing us to send more missions to faraway distances, but also hopefully one day colonize other objects. But
Colonize
for now, we
other
don't really have a
objects.
really good system to do this just yet. Even though originally NASA sort of proposed
Technically, so are we colonized by fucking fungal intelligence? Mushroom spores?
these ideas pretty much 2 decades ago, we still haven't found a very efficient way of doing this. So in some sense, this image right here is still a little bit of wishful thinking.
It is.
We kind
You
of
gotta get
wish
some
we knew how to
fucking
do this,
tech.
we just don't know how to do this yet. But that's of course why we're so
I
excited
don't.
to have papers like this, and hopefully
Someone
other
might
scientists will
have some
pick up from
shit
there and discover
come
how to
through.
do this a lot more efficiently with a lot more precision. But until then, that's all I wanted to mention in this video. Check out the papers in the description below, subscribe if you still haven't, share this with someone who loves learning about space and sciences, maybe come back tomorrow to learn something else, and maybe support this channel on Patreon or by buying
Thanks, bro.
a wonderful person t-shirt you can see me wearing right now. I'll see you tomorrow, peace out, and as
I'm
always,
wearing
bye-bye.
my wonderful person t-shirt. That's insane, dude. Okay.
You absolutely love your dog.
Yes.
And you're not afraid to show it.
No.
But all the toys, comfy beds, treats, and fancy
I don't
collars
even-
can't let your pet know just how special they are to you.
I agree.
In this video, we'll
fucking
show you
trippy.
9 ways to tell your dog you love them.
9 is the
in a
God
language
number.
they're sure to understand. Number 1. Put down your phone when you walk into the house. Your dog needs some face-to-face interaction with you when you come home. This is because they don't know what a cell phone is, but they do know they don't want to compete with it. That's why the
Wow.
first way to tell your dog you love them is to give them your full attention when you walk in the door. Oftentimes,
Humans.
when we are with our dogs, we are staring at our phone at the
Holy
same time.
fuck.
Whether you're on a walk around
It's
the
like
block
humans.
or snuggling on the couch,
2
it's
kids
best to
and a
give
dog.
100% of your
Look at
attention.
this dog.
Oftentimes, when
This
we
dog
are with our
probably
dogs,
isn't
we are staring at our phone at the same time.
Able to
Whether you're
go at home on the couch. You can tell he's like a little
on a
like
walk around the
he's like, you really humans sit on this doctor ass stiff couch?
block or snuggling on the couch,
They- I
it's
don't
best
even-
to give
those aren't even
100%
my- those
of
aren't
your
even my
attention to
people.
your pet.
I'm an actor.
Number 2, respect your dog's nature. Many dog owners confuse caring for their dogs with treating them like babies. It's important to remember that a dog is a dog, and we need to respect their singular needs. Many dog owners discourage their dogs from certain inherent behaviors, such as eating dirt, sniffing urine, and sniffing each other from behind. In these situations, we are not caring for our furry friends, but preventing them from their own nature. This can cause anxiety and confusion.
Wow.
It is important that you love your dog for who they are.
Let him sniff.
Number 3,
butts.
rub their ears. Dog experts say that the ears of a dog are one of 3 nerve centers in their bodies.
Okay.
When you rub a dog behind the ears, a sense of pleasure goes through their entire body.
No shit,
This
right?
is extremely relaxing. Just like when you rub their belly.
It's like humans
Another
when they
part of your
listen to
dog that
shit.
has extremely sensitive nerve endings. That's why when you rub the ears of your
Insensitive.
dog or rub their belly, they close their eyes and drift off into doggy heaven. Oh, and did we mention the other nerve center for a dog's pleasure is between its toes?
Wow.
Number 4, lean in when you talk to them, but don't smother them with affection. The best way to tell your dog you love them is to lean into them, and then let them lean into you. Even though it's tempting, full body hugs aren't good for dogs. A hug is usually threatening or unwelcome to them, especially if they feel trapped. Leaning into a dog and then letting them lean into you is a much better way to bond.
Yeah.
Displays of affection like this are often overlooked and confused with other behaviors, so don't ignore their hugs.
Cool.
Lean back on them for a moment and let them know you love them too.
I fuck with
Don't
that.
push them away or crush them. Just the right amount of lean will demonstrate that you trust them. Number
Lean.
5, look into their eyes. According to researchers at Duke University, you should make eye contact with your dog when you are cuddling with them. Studies have shown that making eye contact while cuddling with your dog releases a hormone in them known as oxytocin.
Wow.
Oxytocin,
Give 'em
also
the
known as the
oxys.
love hormone, literally bonds you with your dog like a mother and baby. So the next time you and your dog are snuggling, look them right in the eye.
Give 'em
They will
oxys.
bond with you like you never thought possible. Number 6, prepare their favorite food. Feeding and love go together perfectly when it comes to showing your dog you love them. So it should be no surprise that
How
if you
do
make
you
a
know their
special dish for
favorite?
your dog, they will love you for it. And this doesn't mean feeding them table scraps, which can eventually harm your dog's health, or feeding them too many treats,
Grandma-
which can also make them overweight. Preparing a meal for your best friend is also a great way to tell them that you love them too. Number 7, raise your eyebrows when you see your dog. This is another way to show your dog you love them. It's one that comes from Japanese behavioral scientists. They explain in their research that when a dog raises their eyebrows and sticks out their tongue, they are relaxed and happy. Believe it or not, your dog expects the same from you. Scientific studies have shown that dogs can differentiate between human emotions from facial expressions.
Really?
You can try to hide your feelings, but your dog can read your emotions from what's written on your face.
Shit.
So greeting your dog at the door with raised eyebrows and a relaxed smile shows your canine how happy you are to see them. Number 8. Talk to your dog using your dog voice.
Yeah,
A study published in the Journal of Science found that dogs understand a little bit more about human speech than we think. Believe it or not, when scientists studied dogs using an MRI scanner, they found something interesting. That dog recognized not only words of praise, but a praising voice as well. So, dogs will not only listen to the tone of your voice, but the words of praise at the same time.
Wow.
They're a little bit more perceptive than you think. So, your tone of voice and choice of words are another one of the 9 ways you can literally tell your dog you love them.
Okay.
Number 9. Let your dog snuggle with you when you get the chance. Snuggling is awesome for dogs, but never go in for the big hug because they think you might attack them. But they do like to cuddle. So whether you let them on the couch or into your bed, they like to lie with you and just relax. The close contact brings them closer to you and lets you show them that you love them. And if you don't want your dog in your bed or on your couch, it's okay. Binge watch some TV from your beanbag chair. They will probably put their paw on you in appreciation until they sleep soundly and contentedly. This is because you have gotten down to their level and showed them how much you love them.
I love my people on Earth. Thank you for that video. Alright, this one will be good.
Infinity. Infinity.
And beyond.
Infinity.
What is infinity?
Infinity is really cool.
It's about as big as it gets.
You can't really put a name to it because that limits it.
Chris
Infinity,
Payne is
as I
infinity.
see it, refers more to
Philosopher
the true nature
Chris
of reality.
Payne is
No
reality.
one and no thing has any kind of separate, inherent,
Whoa,
intrinsic
hold up.
nature. Thing has any kind of separate.
No one and no thing has any kind of separate, inherent, or intrinsic nature. Agreed. I'm just this form. I'm right here. This is me, yo. Tried to leave, but here still. Didn't even really try to leave. I just fucking go to sleep and wake up.
Inherent or intrinsic nature.
I am nature.
I'm a librarian, so I feel that infinity is my business. I connect words that were written 1,000 years ago.
Same.
Also words that were written last week.
If there's an
Yep.
infinite number of possibilities, it means I have no limits as a composer or a performer. Every
Right.
single note that I choose to play in a song,
Right.
I could have played any of the other notes or the notes between the notes.
Facts.
You know, like in the blues.
Infinity is something that just goes on and it's continuous. It does not have an endpoint.
I can show you
Oh,
my experience of infinity.
please demonstrate. Good one.
Infinity means numbers go on and on.
Infinity, generally speaking, is a very precise mathematical concept.
Infinity is a pure fiction, an optical illusion. Before Einstein, people believed that the speed of light is infinity, it's instantaneous. And then Einstein explained it into relativity theory, that the speed of light is finite. It's very, very fast, the light, but it's still finite. So analogously, the largest integer is very, very big, much bigger than the speed of light. But analogously, the largest integer is very, very big.
Integer is very, very big.
Much bigger than the speed of light, but still finite.
So what we will be talking about we want to call a near infinity. It's something which actually does take place in our finite world, but it's so big and complicated that complexity of it is approaching infinity in practical terms.
Now that we have computers, it's time to get rid of this illusion and start and doing completely, purely finite and discrete mathematics.
Infinity is there to stay.
I've spent years thinking about it.
I have.
And I'm no wiser.
No, Mom, I'm not an accountant.
Nope, fuck that.
This is what we do. Right? We deal with stuff like that. We deal with questions like that. This is why people like me go into mathematics.
Yeah.
We've got these different perspectives we're going to be investigating tonight. We've got infinity looked at from the point of view of philosophy, theology, mathematics, and physics. And we're going to try and wrap ourselves around all of that in the next 90 minutes. So sit back and enjoy the ride. Okay? We're going to begin with Philip Clayton. Philip's a philosopher, theologian. He's a provost of Claremont Lincoln University. He was a principal investigator of the Science and Spiritual Quest program. He's written more than a dozen books in this field, including Adventures in the Spirit, In Quest of Freedom, and Religion and Science, The Basics. And he's spoken about this all over the world.
He's a book
Philip,
writer.
take us from what we've just seen.
Chris Payne.
Infinity, what an incredible concept. You can picture the earliest men and women staring up at the innumerable stars or watching grains of sand slowly slide through their fingers and think, what is this thing without limit? I want to take you on a brief little stroll through the history of
Am I really going to watch this?
Try to do that in a finite period of time.
Right. Shit.
5
you
minutes.
caught me quick.
Let's see if... Yeah. Keith's going to watch me.
Wow.
Let's see if I can find a couple of philosophers, a couple of theologians, maybe a representative of East and West.
Yeah, I'll represent
give you some
both.
sense of the parameters of this concept, if that's not a contradiction in terms. In some ways, a vast variety of ways of conceiving of the infinite. In another sense, a few core concepts that keep arising that you'll see over and over again as we move through this evening. Let's start with Zeno of Elea, the philosopher who gets credit for first introducing the concept of the infinite in the West. Actually, that's not quite right, because Anaximander had introduced the concept a few years earlier of the boundless, apeiron, the thing that's without limits, a scary kind of notion that the Greeks really disliked. You can't build a Parthenon with the boundless, right? Zeno found that whenever he introduced real infinites into the world, he ran into paradoxes.
Wow.
So let's take the fastest Greek of all, Achilles, and let's set him in a foot race against a tortoise, right? Can we give the tortoise a head start? Is that all right? Right.
No.
So the tortoise is out there in front. An hour later, he's made 100 feet, right?
An
and
hour
here goes
later?
Achilles. Zeno says, well, he's got to go halfway to the tortoise first.
Okay.
And then he's got to go halfway between there and the tortoise. And then he's got to go halfway. You get the point? Achilles, Zeno argued, could never pass the tortoise.
Right. That was my...
infinites are real. Because he always has to transverse half the distance and half the distance ad infinitum, right?
Wow.
To the end. So the infinite and paradox are linked from the very beginning. Let's move on to Pythagoras. We give Pythagoras credit for inventing the notion of mathematics, which, by the way, in Greek means that which can be learned. He did it with a quasi-religious orientation. The Pythagoreans said that each integer has some sort of philosophical or spiritual meaning. And the ratios between the integers are crucial.
Wow.
7/8, 1/4, and so forth. So the harmonic progression was for them a religious insight.
he launches the idea of the theorem, and what's the most famous theorem from Pythagoras? The Pythagorean theorem,
wow, right angles.
And all of a sudden, the whole project goes to hell in a handbasket. Right? We've got an equal right angle triangle, 1 and 1. So we see 1 squared plus 1 squared, 2, right? Equals c squared. So c equals the square root of 2. But that is an irrational number. To write down the square root of 2 would take us infinite digits with no repeating pattern, right? Right in the middle of the religion of the infinite breaks out the impossible, irrationality. The religion of rationality shot to hell.
This is irrational.
Right at the outset of the story. Let's step over to India for a moment and see how things look different over there.
Hey, okay.
Go to the great founder of the Jain religion. You know, Ahimsa, Martin Luther King, Gandhi, Mahavira. The Jains weren't famous just for that, though. They also did incredible speculation on the nature of the infinite. As far as we know, by 400 BCE, the Jains had used
by 400
that hadn't been used before. The difference between that which goes on without ending and the truly limitless, the truly endless. They also began to distinguish.
I had an amazing friendship with this girl whose last name was Jane, and she was Jainist, and I got into the depths of this, so he's really hitting me home.
Orders of infinite. So there's infinite in length, infinite in area, infinite in volume, and infinite perpetually.
That's because I have love.
Get the distinction? They're trying to give us orders of infinite as they go.
Wow, right.
The
I'm
last
trying to
thing
give
for
you...
which we credit the Jains, when they distinguish between innumerable, and infinite, they said the highest enumerable number, n, and they defined it the way that, as we'll hear in a moment, Cantor defined Alf null, the first number of the transfinites. So amazing comprehension in India some 2,400 years ago.
Right.
All right, let's step back to the Greeks and come to Aristotle, the father of some 24 sciences, that crucial thinker. Aristotle realizes that with actual infinities, we are in deep doo-doo. Basically, physics is not going to work well. So what he decides is that there exist no actual infinites. We have to banish that concept from the physical world if we're going to do good science. So he says it's fine that we can have a potential infinite, it just can't ever be actual. So for example, the potential infinite is start counting upward. You can go as long as you want to, but in a finite period of time, you only make it a finite distance. The world is only a finite number of years old, therefore, there are no actual infinites. Take a quantity and start dividing. You can divide it as much as you want to, but at some point you'll run out of time, as I'm about to, and you have to stop.
Right,
Aristotle
you stop.
launched this notion of potential infinite. All right, let's finish off with 3 theologians and 3 radically different understandings of the infinite. Let's go to the high Middle Ages, the scholastic period, and that greatest of thinkers, Thomas Aquinas. Thomas Aquinas says, as a theologian, I'm interested in a different question. Y'all are interested in quantity. I'm interested in a quality of existence. What mode of existence would God have? The divine. God would be qualitatively infinite, which means God would be ens perfectissimum, the most perfect being. It's a mode of existing. It's a way of existing that sets God apart from anything else, not quantity. So he bifurcates between the mathematical infinite and a religious or philosophical infinite.
Philosophical.
But still Aristotle
kind of
rears his ugly
neurological.
head, because even this infinite God couldn't create an infinite object, because anything in the world must be by nature finite.
Wow, right.
Moving on from Aristotle to the 15th century, we find the Bishop of Cologne, Nicholas of Cusa.
Of Cologne.
And here's a theologian who decides He's going to go with the infinite all the way, no restraint. So the infinite,
Yeah,
what
that's
is
why
that?
I made a joke about
It's
cologne.
that thing which has no limits.
Right, humor.
Therefore, everything must be included within the infinite.
Humor.
Nothing can be excluded.
Humor.
The world itself must be within God. Heresy, I know, it almost cost him his job.
Yeah.
Mathematics love Nicholas of Cusa because he used mathematical examples to describe the God-world relation. So
Oh, shit.
God is the circle whose center is everywhere
Yes.
and whose circumference is therefore nowhere. Nothing is outside of God. And he said if you get that right, it means a coincidence of opposites. God, world. God, humankind linked together. And he said we are the animal that stands at the boundary between the eternal and the finite. And finally, let me close with that great heretic.
Wow.
The one that the modern thought loved to hate, Baruch de Spinoza. A Jewish, fascinating Jewish philosopher kicked out of the
Wait, hold up. Why did he
the
say
modern
Jewish?
thought
And then he
loved to
said
hate.
he had to say fascinating Jewish. He must feel some type of way.
Baruch de Spinoza, a Jewish, fascinating Jewish philosopher kicked out of the synagogue at age 14 for allegedly saying that God has a body. Spinoza decided to write his metaphysic in the guise of geometry.
Wow.
Etica more geometrico, ethics in the guise of geometry. And you guys, it's overwhelming, compelling argument. If God is infinite, God is the one substance. There can be no other substances besides this one.
Mm-hmm.
The substance must have infinite attributes. And we, finite little beings, can't be separate beings, so we must be modes of the one. God, however, is not the transcendent God, the personal God who does stuff. He used the phrase Deus sive natura, God that is nature. God and nature become absolutely one for Spinoza. And the highest ethic is for you to live in accordance with the laws of nature.
Yes.
To be a part of that one unfolding infinite whole is our fate. Half the philosophers revere him as science-friendly. Half the philosophers revere him as theological. For him, it is the intellectual love of God to know nature, to know yourself as part and parcel of nature, and to behave together with nature.
Right.
The infinite then focuses Spinoza from theology back into the natural world.
This infinite
So,
thing's
a
supposed
short
to be
history
into
of
the
infinity.
natural world.
Okay. Thank you.
Or else I
Makes me
wouldn't
feel
fucking
nervous.
give
I mean,
him
we're
90
live
minutes.
streaming this. I'm not quite sure who's listening in to this broadcast, but as a simple mathematician, I'm feeling very nervous there. And I'm going to very rapidly bring it back to my own comfort level, because my next guest is a regular practicing mathematician like myself. It's Stephen Strogatz, one of the world's most highly cited mathematicians. His honours include a Presidential Young Investigator Award, a Lifetime Achievement Award for the communication of mathematics to the general. One of the world's most highly cited mathematicians. His honours include a Presidential Young Investigator Award, a Lifetime Achievement myself. It's Stephen Strogatz, one of the world's most highly cited mathematicians. His honours include a Presidential Young Investigator Award, a Lifetime Achievement Award for the communication of mathematics to the general public, and membership in the American Academy of Arts and Sciences. He's currently a professor of applied mathematics at Cornell, and his publications include Nonlinear Dynamics, The Calculus of Friendship, and, wait for it, The Joy of X. Stephen.
Thank you. Thanks very much, Keith, and thank you all for coming out. I'd like to, yes, as Keith said, bring it back to mathematics. And for us in the math world, the really great transcendent hero of infinity is Georg Cantor. Cantor lived in the mid-1800s and came up with ideas that are so mind-blowing and so stunning that we're still kind of reverberating from his insights. We'll be hearing about the disturbing things that he thought of, that are still so counterintuitive that the mathematicians and physicists are really grappling with them even today.
All right.
So the big insight from Cantor, the biggest of all, is that there are different kinds of infinity. Some infinities can actually be bigger than others. So I want to walk you through a few of his mathematical arguments because they're so beautiful and so elegant that if you haven't seen them, I think they'll change your life. And if you have seen them, this is like listening to the greatest song, your favorite song, a second time. I don't think you'll mind. So, but to set this up, I want to.
This is literally
I'm going to show
like
you some visual
listening
versions
to
of
my
what
favorite
Cantor
song
came up
again.
with. But first, I think it's worth mentioning a little bit about his life because it was, as with any great maverick, there were people who opposed him. He was not regarded necessarily as a hero to all mathematicians. In fact, one of the greatest mathematicians of his era, Henri Poincaré, described Cantor's work as a disease. Ouch. Another one of his colleagues, a mathematician named Kronecker, who was in a position of power in Berlin where Cantor very much wanted to be a professor. He never got to be a professor in Berlin. Kronecker wouldn't let him. Kronecker described Cantor as not only a charlatan, but a corrupter of youth. Now, I don't know what that makes me, since I see there are some young people here, and I'll be talking about his work. So, yes, corrupter of youth. Well,
Corrupter of youth.
actually, this was no joke for Cantor, because he, as it turns out, suffered from mental illness. It seems that he had we know that he did have very significant bouts of depression, may have had bipolar disorder, and he spent quite a few stints in sanatoria.
That had nothing
It used
to
to
do
be
with
thought
it.
that it was because of these attacks from mathematicians that he was driven to this, but I mean, in more modern thinking, probably he just had, he suffered from depression, but it didn't help that he was taking this withering criticism from so many people. On the other hand, some of the other great mathematicians of the time, like a man named David Hilbert, probably equal to Poincaré in greatness as the two greatest of that era, Hilbert described Cantor's work as a paradise and said nothing will ever expel us from this paradise that
Right.
Cantor has created. So let me introduce you to Cantor's paradise.
Wow.
First by showing you some of the paradoxes and really startling things that come about when you start thinking about infinity mathematically. And the way we'll do this is with a charming video that was produced by the Open University a couple years ago.
60-second adventures in thought. Number 4, Hilbert's Infinite Hotel. A grand hotel with an infinite number of rooms and an infinite number of guests in those rooms.
Right.
That was the idea of German mathematician David Hilbert, friend of Albert Einstein and enemy of chambermaids the world over. To challenge our ideas about infinity, he asked what happens if someone new comes along looking for a place to stay. Hilbert's answer is to make each guest shift along one room. The guest in room 1 moves to room 2 and so on. So the new guest would have a space in room 1. And the guest book would have an infinite number of complaints. But what about when a coach containing an infinite number of new guests pulls up? Surely he can't accommodate all of them. Hilbert frees up an infinite number of rooms by asking the guests to move to the room number which is double their current one, leaving the infinitely many odd numbers free. Easy for the guest in room 1, not so easy for the man in room 8,600,597. Hilbert's paradox has fascinated
Yeah.
Mathematicians, physicists, and philosophers, even theologians, and the infinite number of rooms, two, and so on, to make each guest shift along one room. The guest in room 1 moves to room 2, and so on. So the new guest would have a space in room 1, and the guest book would have an infinite number of complaints. But what about when a coach containing an infinite number of new guests pulls up? Surely he can't accommodate all of them. Hilbert frees up an infinite number of rooms by asking the guests to move to the room number which is double their current one, leaving the infinitely many odd numbers free. Easy for the guest in room 1, not so easy for the man in room 8,600,597. Hilbert's paradox has fascinated mathematicians, physicists, and philosophers. Easy for the guest in room 1, not so easy for the man in room 8,600,597. Hilbert's paradox has fascinated mathematicians, physicists, and philosophers, even theologians. And they all agree you should get down early for breakfast.
It's a brilliant video. I hope you caught the main mathematical points at the risk of over-explaining. I'm just going to remind you what you saw. That in Hilbert's Hotel, which is this parable of infinity, first of all, the Hilbert Hotel always has room, even when it's full. It has infinitely many rooms, and so as it was explained, if another guest shows up, you can still make room for that guest by shifting everyone over one room. And there's always room because there's infinitely many rooms for them, and then the new guests can go in room 1. If a bus, or as the video says, a coach, even a bus with infinitely many new guests is still not enough to cause trouble at the Hilbert Hotel because you can shift all the current guests into the even rooms, leaving the odd-numbered rooms for the guests. So the question starts to become, it's leaving the odd-numbered rooms for the guests. So the question starts to become, well, if infinity is really that big at the Hilbert Hotel, is there any number of guests that you couldn't accommodate at the hotel? I mean, are there infinities so big that even the Hilbert Hotel would not fit them? So Cantor worried about this and came up with an attempt to find an infinity too big even for, I mean, he didn't think in terms of the Hilbert Hotel, but let me illustrate it that way by imagining a situation that if you're kind of a nasty contrarian, you might think, what if an infinite number of buses, each carrying an infinite number of people, show up? What will the night manager do with this? So let me illustrate. In fact, that problem can be solved at the Hilbert Hotel. That's no problem at all. And so here's the solution to it. Let's first visualize these people by showing a picture which will have a row containing all the infinitely many guests that would correspond to bus number 1, and then there's bus number 2, each with its infinite number of guests, which I'm going to depict as faces. And then there's an infinite number of these buses. So there's the first image. It's not supposed to just be 4 by 4. You're supposed to picture it with infinitely many guests in each row and infinitely many buses.
Right. Can't see, but from my close position, I can see some dots at the end of those rows. The infinity dots.
Yes, thank you. Right. So those 3 dots are supposed to indicate that both the rows and the buses go on in all directions. All right. Now, a first inexperienced manager might attempt to solve the problem this way. I mean, what the goal is to assign each passenger a room. And the problem will be solved if, for any given passenger, you can say that person is in a room with a finite number, a specific number. Like, imagine a guest list, and I can say, oh, yes, Mr. Smith, you're going to be in room 133. As long as everybody has a room, everybody's happy. Here's the first attempt to put people into rooms. Let me put person 1 from bus 1 in room 1. And then I'll put the second person from that same bus in room 2 and the third person in room 3. You can see this is not a good solution. Do you see what the problem is?
No.
No one in bus 2 is going to be happy because the whole hotel will be filled just with the passengers from bus 1, and so you'll have infinitely many bus loads of infinitely many unhappy people. This is not what you want at your hotel. So that is not a good solution to the problem, but there's a much more clever way of doing it, which then does actually accommodate everyone. What you do, notice this zigzagging pattern of arrows. You start with the first person, that person gets room 1. The second person is at the end of the first arrow. So that would be passenger 2 in bus 1. Then you go down to bus 2, passenger 1, that person gets room 3. Just follow the arrows, and that's the order in which people are placed into rooms. Can you sort of see what's happening, how it's fanning out from the corner? And that will have the property that you can pick any person in that infinite array, and that person will be served in a finite time. They will have a room.
Wow.
So this is a way of actually accommodating infinitely many people in infinitely many buses in the Hilbert Hotel.
So that's sort of
this
what
raises
the Bible did.
Oh, by the way, I should say that
Bible
there's the
is-
abstract version of this, which is that this shows that the fractions, the positive fractions,
The Bible is
starting, like
Hilton Hotel,
not starting,
in a way.
but think about any fraction: 1/3, 1/5, 2/8. Don't worry about lowest terms, 4/17. Any fraction you can think of would correspond to one of these passengers, like the person in bus 4 and passenger 17. That might be what we would call 4/17. I mean, there's a correspondence between the people in these diagrams and the positive fractions. And so this argument that I've given you here is essentially Cantor's argument for showing that the positive fractions can be counted in the sense that they can be put into what Cantor called a one-to-one correspondence
Right.
with the natural counting numbers, the numbers 1, 2, 3, 4.
Uh-huh.
That is, there's a way of listing all positive fractions so that we can say this is the first one, this is the second one, this is
Right.
the third one, and every positive fraction will be at some finite place in that list.
Yeah.
They're not ordered by size, by the way. They're ordered in this way that I just described with this zigzagging pattern. So the rational numbers, the fractions, are countable, meaning they can be put into one-to-one correspondence with the natural numbers, 1, 2, 3, 4, and so on. And this raised the question in Cantor's mind. It seems like everything he could think of is countable. Every infinity he could think of was countable. Or to put it another way, the Hilbert Hotel really lives up to its motto. There's always room at the Hilbert Hotel.
There's always room at the Bible.
Well, actually, though, in 1873, Cantor discovered an amazing example showing that was not true.
Right.
That there's an infinity that is so big that it would defeat the Hilbert Hotel, no matter how clever the manager is.
Wow.
And this has to do with the amount of infinity contained in a continuous line.
Wow,
If you
no, I
imagine the
showed
number
up here.
line, the traditional number line that was tacked on the wall of your elementary school.
Yeah, fucking BCE is how we create our dates.
Shows the integers 1, 2, 3, 4, and there's all the space in between where all the fractions are and all the irrational numbers. That continuous line, what we think of as the real numbers, if the real numbers showed up at the hotel, there wouldn't be room for all of them.
Facts.
And here's the proof. This is Cantor's famous diagonal proof. He said, imagine that there was a roster, a sort of a guest
Not
list.
everybody could be.
And this was
Whoa,
a guest list.
What?
It's going to be a proof by contradiction. I'll show that there's a real number that doesn't have a room. Here's a putative list where room 1 is assigned to this real number that's being shown here, 0.42, etc. And room 2 is assigned to some other real number. Don't worry about the details of the number. The idea is just that there was a list of all the real numbers, just like we could list all the rational numbers. Maybe we could list all the real numbers. Well, Cantor's argument is no, because if there were such a list,
We can't list
here's an
numbers.
attempt to show what it might look like, you then circle the first digit of the first number. I don't know if you can see, there's a little circle around that 4.
4218.
And then you circle the second
K-Paint
digit of the second
8.0.
number, 2, and the third digit of the third number, 1. So from that, you construct a real number, which in this case would be 0.421, and so on. That's not the problem. That's not the bad number.
8.0.
What we
He doesn't
then
want
do
to say
is
it.
change each of those
I'm not
digits
the
in
bad
that
number. You want to
like
change
the 4
me.
that begins this number, maybe make it a 3, or just whatever you want. Just change it.
Right, yeah.
Or the 2,
Update me to
that's
be
the second digit, make it something else. Make it a 7. Just have some system.
Right.
But the rule is
Having a
construct
system,
this number
yeah.
down the diagonal, and then you systematically change its nth digit
Yeah,
to something else.
right.
That is, if it's the nth number, its nth digit gets changed. And so by doing that, Cantor
Right.
constructs a number which is not in the list.
K-Paint 8.0.
Because it can't be the first number in the list because it differs from the first number in the first place. It's not the second number in the list because it differs from the second number in the second place, and so on. So by systematically going
K-Paint is
down the
my name,
diagonal
I
and then
gave my
changing every digit,
body.
he has now produced a number that is not on the list.
Facts.
And this argument
Is how we
shows
created
that,
numbers.
in fact, the real numbers cannot be counted.
Real
There is
numbers
no
can't be
list that
counted.
can embrace them all.
I'm a real
And so with that comes the
dude.
question then, this very nagging question that we're going to be talking about next, which is, well, if there are now two kinds of infinity, the countable kind and this continuous kind, which is bigger, are there other infinities? And really more to the point, is there some infinity that's sandwiched in between them? Is there some infinity smaller than the continuous infinity but bigger than the infinity of the 1, 2, 3 variety? That's called the continuum hypothesis, the idea that there is no such infinity in between.
Wow.
It was Cantor's great conjecture, but he never proved it.
Mm-hmm.
maybe Keith will tell us a little bit about his own experience with the continuum.
Yeah, because early on in my career, I actually went into set theory because I got seduced by what happened next. And here is what happened next.
That's what set theory is. I'm watching a video. This is set theory.
Called Kurt Gödel, showed that this conjecture, the continuum hypothesis, that there is no infinity between the natural numbers and the real numbers, Gödel showed that conjecture could not be proved false. Okay, you might say, it means it's going to be true, right?
No, I could shut this video off.
No, because in 1963, an American mathematician called Paul Cohen showed you couldn't prove that it's true. Can't prove that it's false, can't prove that it's true.
Yeah.
It's independent of the axioms that we take from mathematics. And as a graduate student beginning in the very end of the 1960s, I think it was significant that this was in the 60s. People were high on all sorts of things. High enough to try and go into the infinity.
Yeah.
There was the question of...
Facts.
We suddenly realized that we had a technique. Cohen invented a technique called forcing that allowed us to construct alternative set theories, alternative mathematics, in which you could prove things true, not true, or neither of them. You could prove things independent. And like many mathematicians of my generation, I got seduced by that kind of question. And we used Cohen's techniques in particular, and some of Gödel's techniques, in order to investigate alternate universes. And it was a wild period.
Wow.
But it was a period that was eventually going to get tamed. And it was going to be tamed, at least I think it was going to get tamed. I would say it's been tamed to a large extent by our next guest, who's William Hugh Woodin.
Why is that camera shifting in the back?
He's a set theorist at the University of California, Berkeley. There's a type of large... Actually, I should be careful. Large cardinal in my business does not mean a large portly gentleman in a red uniform. That's his business. A large cardinal is an infinity. It's an infinity of a very large size. So Hugh Woodin has a large cardinal named after him called the Woodin cardinal. He's made many notable contributions to the theory of inner models and determinacy. I think of him as the mathematical equivalent of physics' Ed Witten, who's invented 21st century mathematics that dropped into the end of the 20th century. Hugh, take us from there.
All set. Thank you for that
A
introduction.
New World Songbird.
So I've spent my life trying to solve the continuum hypothesis. Now, we just heard you can't prove it true, and you cannot.
I am a cardinal, a New World Songbird of the Bunting family.
It just means we don't have all the principles yet.
Because I take bunts and I get safe to first.
Are we missing the key principles, or are there principles defined that will enable us to determine whether the continuum hypothesis is true or false? Or maybe there's a much stronger version of Cohen's theorem that shows that there really is no answer. So really the fundamental question is this. We have this conception of mathematical infinity, and it's embodied in our conception of the universe of sets. Now, that's a human creation. Maybe there's no there. There's no up. It's just entirely an extrapolation of the world around us into a realm where there is no truth.
No.
And not being able to answer the continuum hypothesis is a direct challenge on this. It's the first question you would ask in the mathematics of infinity. And if you can't come up with an answer for that, what sense is there to the subject? So that's the situation. Now, I have to say, when you work on a problem that can't be solved, you're allowed to change your mind.
What sense is it?
That's the great thing about it. So
To not
10 or
change your mind.
15 years ago, following one line of inquiry or an attempt to find new axioms, I showed there was kind of an ultimate solution along this line, and I speculated then in a series of articles that the continuum hypothesis was false. And in fact, there was exactly one infinity in between the infinity of the counting numbers and the infinity of the real numbers. And in any case, I showed there was an optimal solution. But then that solution ultimately doesn't fit into understanding the entire universe of sets. The continuum hypothesis is just one instance of an infinite sequence of questions. And it makes no sense to answer the problem of the continuum hypothesis without having some global solution to the universe of sets.
Wow.
So that became the problem. what could this global solution be? Well, we're at a crossroads right now. There's a series of conjectures, very precise, and the key question is whether these conjectures can be proved or not. If they can be proved, we will have one new principle which, when added to the traditional axioms of set theory, will settle the continuum hypothesis. True, so I'm a traitor to my previous self. And it will resolve all instances of the continuum hypothesis. And in fact, it will resolve all instances of questions which Cohen's method to date has been used to show are unsolvable. So that's kind of one holy grail. Prove these conjectures, we will have advanced our understanding of infinity, and we'll have a conception of the universe of sets that is as robust mathematically as a conception of the integers themselves. That's one possibility.
Wow.
The other possibility is that
because
you refute these conjectures. Then it's utter chaos.
Still
we're back.
chaos.
It's much worse than where we were. So that's where we are. I really am not sure what will happen. Many people have said, and they take the position that the fact that the continuum hypothesis could not be solved is an indication of this is all just human imagination gone wild. You know, and there's some merit to that. I don't believe it, but you know, I got corrupted by Cantor. So,
what do you not believe? Hold on.
On the other hand,
got
many people have said, and they take the position that the fact that the continuum hypothesis could not be solved is an indication of this is all just human imagination gone wild. You know, and there's some merit to that. I don't believe it, but you know, I got corrupted by Cantor. So, on the other hand, if the other picture unfolds, and we do prove these conjectures, maybe we do them in 5 years, maybe we do them in 1,000 years, who knows? I think that will be a remarkable event, because set theory, you don't see it. There's no satellite you can build to go out and measure the continuum hypothesis. You can't go to Europe and say, look for this particle in the LHC. There's nothing in our world around us that's going to help you determine whether or not the continuum hypothesis is true or false, as far as we know. Set theory has not penetrated into physics yet. And if we see that this imagining of this realm far beyond the integers really has content and meaning, and our intuitions guide us to the true principles, I think that's remarkable, because it will be success where there was no reason to expect success. You don't find the answer to the continuum hypothesis by some clever proof. We know you can't do that. Somehow there has to be a solution that forms to our intuitions.
Wow.
There have to be clues. And there's no reason to expect that that will happen.
Right.
It really could just all be a fiction.
It's all empty.
So there's this realm. It's beyond the realm we see around us. Does it exist? And one key question there is
Is
it
it
exists?
existing
The
now?
continuum hypothesis has an answer, and we need to find it. Or we could go the skeptics route and show once and for all that the conception of mathematical infinity is just that, a fiction, and there is no answer. So those are the two futures, and I wait to see what happens.
Whoa!
Touche. So you're living too.
So hands up all those people who are attracted to mathematics because there's always a unique right answer. And it's in the back of the book. Well, it may be in the back of the book, but no one's managed to get hold of a copy of the book yet. So,
Right. Wow, I haven't
it's worth
released my
remembering,
book
by the way,
yet.
that we got.
Yep, say less, dude. And then he goes to the camera behind. I'm out. They're